This is a gas chapter. It's actually chapter 6 in your book. And this is a nice playlist from Dr. Bean if you want to just watch several people talk, one person talking through several videos. This is the overview page, and it may seem like a lot at the moment, but after you finish a chapter and you come back, it's a nice way to pull all of the information together. Right now, we have a few different squares that mean different things. We're going to be talking about pressure, and pressure has several different units. So this section right here, everything that is in bold is a pressure unit. The one here in the States that we are the most familiar with is PSI. That's what you get in a tire pressure readings, things like that. This pressure unit right here, this is what you might hear about on the news if you're hearing the weather and they talk about the barometric changes. That's the pressure unit. It's actually a certain amount of mercury in a tube with a certain diameter, and it's how much the air pressure, it's an open tube on one end, and it's how much the pressure in the air pushes on that tube and moves the mercury from like where it is normal. So that's actually is about moving mercury up a certain millimeter distance. A torr is another unit that you'll see. Torr has 4 letters and millimeter mercury has 4 letters. That's how I used to remember. Those are the exact same conversions. In physics and upper level chemistry, you may come across the bar being used, and then of course there's pascals as well as kilopascals. There's all these different units. The units for the numbers that we're going to be using in this chapter, though, it's actually the easiest unit. It's an ATM, which is an atmosphere. So when we feel really comfortable, all of us humans on Earth, when we're very, very comfortable with pressure, it's a pressure that's 1 ATM. It might be a little more than that, a little less than that, but it's 1 ATM. Other things we need to know for this chapter. We're going back to this section about temperature. You learned how to convert Fahrenheit into Celsius. You just subtract 32 and then multiply it by 5/9 to get it to Celsius. And then you learn about Kelvin. All of the temperature in this chapter is going to have to be in Kelvin. Something else that you may or may not find helpful is right here we have volumes. We have 1,000 milliliters is equal to 1 liter. We also have that 1 milliliter is equal to 1 times 10 to the minus 3rd liters. We have moles. You guys already know that a mole is this many atoms. This reason it comes into play in this chapter is because we'll talk about moles and we'll have a mole of gas molecules and there'll be that many little tiny gas molecules or atoms that are bumping around in a container. Now, you'll see a lot of equations. These equations have quite a bit in common, so don't let yourself get too worried about saying so many equations. You do want to know when to use the 2 different equations. Use this equation when things change, and because things are changing, you'll see that there are like 2 pressure units. See, there's a P1 and there's a P2, or a V1 and a V2, or a T1 and a T2. You're always going to have 2 because it's something that starts at one value and then it changes to another. So you're going to be given probably 5 of the 6 of those variables, and then you have to solve for the other one. Now, the other situation is when things don't change. It's just when you're just looking at a system and you just want to know what is the pressure, what is the volume, what is the, whatever. All of these equations all contain temperature units. We're going to start with this temperature unit. So notice here's a T for temperature, 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 and a T for temperature. That's because gases are very, very dependent on the temperature of the container of the surroundings. They're very dependent upon that. So notice here is our temperature, and like I was saying earlier, it has to be in Kelvin. Here's our temperature, it has to be in Kelvin. Here's our temperature, it has to be in Kelvin, and here's our temperature, it definitely has to be in Kelvin. Now these also all contain P. I'm gonna mark all the P's, so pressures, pressure, pressure, and pressure. These are all pressure. Now, these pressures are different in what their units have to be. So for this pressure right here, both the units just have to be the same. So one can be ATMs and the other can be ATMs, that's fine. One can be PA and the other can be PA, and that's fine. One can be PSI and the other can be PSI, and that's all fine. The problem is if one is in torr and then one is in pascals. Now for the equations under this, the P does have to be a specific unit. So that is something that's different between the two sets of equations. Let's just review volume before we move on. So here's our volume terms here, and this one also has a volume term in it. So for our volume, both the units again have to be the same. For the volume, if they both are the same, if they both are in liters, that's the okay. If they both are in milliliters, that's okay. If they're both meters cubed, that's okay. It's when one is liter and one is milliliter that we have problems. And you have to change one to match the other. So we've mostly finished with the top green square, and we're going to look at the second green square. And the second green square has this extra letter in it. And once we deal with that extra letter, we'll come back and look at the volume. So that letter is this R. R. And this is our R. This is a constant that we're going to have to remember or use. And this constant has different units. It's actually got 4 units in this one single constant. So this is a volume unit. This is a pressure unit. This is a temperature unit. We already talked about all the temperature's got to be in Kelvin. And then this is a mole unit. Moles are represented with N's in this chapter. So if we have a constant that has a certain unit, our related variables that have those same units, they have to be in the same unit for everything to cancel out. So we're going to look back at the pressure that we were talking about a minute ago. Before, they just had to be the same, but in this case, it's really particular. Your volume unit needs to match R. So if you look at the purple R that we're talking about, our volume needs to be in liters. And then if you look over at your pressure unit, that pressure unit needs to match R. And you'll look down over here. Our ATMs is what our pressure unit has to be. Now, N being moles, N is moles, so that's probably pretty obvious. We'll jump over here and we'll mark him. Oops. So that's N. He's got to be moles. But the reason it's listed as the units need to match R is because if you go Googling on the internet, you will find a big long list of all kinds of R's. It's okay if you want to use the other R's. Sometimes it's even useful to use the other R's. But these are 2 different examples of 2 different R's that you might end up using. The denominator units are the same in all 3 cases. And right here, the volume is going to be different. That's a meters cubed, not a liter. And this is a Pascal, not an ATM. This is a liter, so that one's the same. But right here, your pressure unit is a torr. So we do not recommend that you use those R's, but the problems will always still come out with the correct numbers. You're just going to have to do a lot more unit converting to use those R's. So really do recommend using this R value and making sure that all the numbers that you're putting into the equation have these units right here. The liters, the ATMs, the Kelvin, and the moles. These other 2 equations that are lower are related to the first equations. There's some math, you can see how to work between them. A lot of students just prefer to just have the equation and just use it. So just going to review that what we said about the R also applies. For the pressure, the units have to match R, so that means ATMs. And for this pressure, this unit also has to match R, so that means ATMs. Unless you're choosing to use one of the other units. And in both cases, those temperatures are going to match, Kelvin. Now, this big M right here, great big M right here, this is molar mass. You've seen molar mass before. It's not new. That's grams per mole. It's also in this equation right here, molar mass, grams per mole. The reason that this is useful is that if you know that the molar mass of hydrogen is 1.01 grams per mole from the periodic chart, you can solve a problem for any of the other variables. So it's a helpful equation. Last but not least, let's just review the other 2 units. I'm going to review this. This is just mass. This is mass in grams. So if you were given a mass in grams, you can plug it in that place. And then the lowest one might be a surprise to some people. This is a rho, and it actually represents density. And on your sheet, you may have a typo here. This is supposed to be grams per liter. Previously, you were using grams per milliliter for density units, but for this equation, it has to be grams per liter. It's because there's a volume term kind of hidden in here that you don't see. It's tied into the density term. Or it would have to be like grams per meters cubed, but if you use that one, you're going to have to be going with like this R. So really do recommend the grams per liter for your density. All of these are plug and chug kind of equations. So the idea is that you always know R. So you always know R. T, you probably will get it in Celsius, and you've got to come change them. So you might know T. And then you'll know N and V, you'll have to solve for P. Or maybe you'll know P and N and have to solve for V. Or maybe you'll know P and V and have to solve and N and have to solve for T. All the equations work like that. You'll know like 4 of the 5 terms, and then you'll have to solve for the missing one. And we'll do some examples of these problems. All right, so there's also something else. It should have a great big, huge, bold color around it, and it's STP. So sometimes we get tired of continually saying the same temperature over and over. If you ever see STP in a problem, it's our way of being able to get away with not saying what the temperature is. This is the temperature at STP. This is the pressure at STP. So STP is a way of hiding those two numbers. So now you know if you ever see STP, immediately write in those two numbers into the problem. Now, since you're previewing this class, you should try out these 2 simulations. This simulation, just to make sure that you can see how to work it. I'm going to click on Ideal. When you pump in, those are little gas molecules, and you can see what happens like when the pressure reading starts. I'm going to restart it. So look, it's at 0. It's at 0, 0. Oh, all of a sudden it changed. And you'll see it kind of gets to a steady state. At what point did it change? So play around with that. You can also change to like a littler molecule and get smaller ones in there. You can also mix them. So play around with that for a second. See if you can get this figured out and answer those 3 questions. And then this simulation here, this shows it's like how you mix things. And so again, let's give it like 20 particles on one side and 20 on the other, and see what happens when you push that green remove divider button. And you can describe what happens. And then a fusion is where you're mixing through a tiny hole. And just see if you can imagine what happens. We'll show in class what happens with that one. We do have ideal gases. There are 3 ideas behind an ideal gas. This is in the top hat also. There's a whole video about this. Gas size is negligible compared to the size of the container. So it's basically like you're imagining they're teeny, tiny dots that are so small they don't matter compared to the size of the room or the container or whatever's that is holding them together. Also, they have an average kinetic energy. And this is not the same thing. Velocity is like how fast something's traveling. Kinetic energy takes into consideration the temperature. It's proportional to the temperature in Kelvin. So it's not exactly the same thing. But we do know that as you increase the temperature of a gas, it becomes more and more pressurized. And that's related to the molecular theory of gases. Also, we assume the collisions are elastic, and so there's no energy lost to the walls or friction. But this is the biggest reason why we assume they're elastic, is that there's something called attractive forces, and they're kind of a big deal, but we're assuming they're not there because it makes the equation really complicated. So why calculate with ideal gases? You're going to find out there actually aren't really that many ideal gases. We can still get kind of close to the right number. That's one reason, but the bigger reason is look at how messy this is. This is the equation. P times V equals nRT. This is the equation that we're going to be using today. And look how messy all this is. A is like a constant, and it's specific to every particular gas. So it changes depending on what gases that you're using. So those are constants. And then N is more moles. But the whole reason we have these extra terms is because there actually is a problem with this third point right here. So if I call this point 3, right here, this whole section here, this is a way to fix for attractive forces. Because when the gas molecules are getting near each other and they bump off each other, plenty of the time, just a little bit of their electrons notice the other gas molecule's nucleus and they're like, hey, what's up? And they pause, or just for a split second, there's a little bit of a change and there's not a completely elastic collision. That fixes that. And this section right here fixes for point 1. So this is point 3, and then this is point 1. That the gas sizes, the gases actually do take a tiny bit of space up. They do take up a tiny space. But who wants to use this great big annoying equation? So we're not using that big equation, just pointing out that this is kind of an assumption and this is an assumption. And this makes it so that this ideal gas equation doesn't work at extremely high temperatures. Sorry, it doesn't work at extremely low temperatures. Let's move on. Let's see if we can use these equations. I'm going to show one example, and then you go back and work some of the other ones.